Welcome back, chat. Today's lesson's gonna slap, no cap. God, he's cool. Just Kendrick Holloway up here. All right, so looking at this, we have been dealing with sines and cosines like a lot. I want you guys to go around, and I'm gonna write it on the board, but you don't have to write it on your notes. I want you to write it on your unit circles. I want you to give me the tangents. Find me the tangent of every single point on your unit circle, and then if you have a unit circle here, and here's your point, that's way low, but that's all right. Root 3 over 2, comma 1/2. Out here, I want you to give me the tangent. Cool. Do it until you see a pattern, and then let's start using the pattern. Okay, adding the tangents to your unit circle is the first task, and as you're doing that, I'm going to get my notes set up. You guys just went around, and you should do the whole unit circle, but you should have only found 5 total possibilities for things to spit out as. Now, before we start putting them, just verify for me. Somewhere you get a root 3. Somewhere you get a 1. Somewhere you get a root 3 over 3. What are the other 2 possibilities? 0 and one more. Undefined. Okay, how do we define tangent? Y over x, or give me the trig answer.
OA over opposite over 3.
So give me another trig answer, because I agree with that one too. That's what I just heard. Sine over cosine. Now, based on these, just right here, can you tell me what's bigger, sine or cosine? Are you sure? Are you sure? Why sine? Or why is cosine bigger? Root 3 over 2 is my cosine, and this is a sine, right? I'm further right than I am up. That's what I use. Now, knowing that tangent is sine over cosine, I want you to help me, and you don't have to write this down yet, but I'm going to throw in some of these random answers. Undefined is one of them. Somebody else had 1. We had 0, we had root 3, and we had root 3 over 3. Okay, the undefined one we can't rank. Of those 4 numbers, can you tell me which one's the biggest out of all of them? I think I heard 3 different answers from 3 different people. Root 3 is the biggest of them all, I think. Because I know root 4 is 2, so that must be like, it's not quite 2, but it's pretty big. Everybody agree that this is the biggest. What's the next biggest? 1? Ooh, how would we determine what's bigger between those 2?
Root 3 that has to be less than 3.
Yeah, do you agree that 1 we could be written as 3 over 3? And then if we want to compare the size, what's bigger, 3 or root 3? 3, I think this is bigger. How about this is then the 3rd, right? And the 4th. Are you guys okay with the logic that we just used? Okay, one more time with the tricky answer, not OA. What's tangent?
Sine over cosine.
So the bigger the y value, the bigger the tangent. Do you guys agree with that statement? Because it's the numerator. The bigger the numerator, the bigger the whole number. So check it out. Which of these 3 values right here, I guess 4 values if we put that on, which of these has the bigger y value? The top one, right? Now, this is the one weird little spot. What's the tangent of this value? Sine over cosine is 1 over 0. It's undefined. Okay, bummer. Which of these 3 that are still here have the larger y value? That's supposed to be a root 3, isn't it? This is the biggest one, right? What was the biggest number here? Do you guys agree with that conclusion? Okay, the second biggest number was what? 1. That's the second biggest y value. And the smallest number is root 3 over 3. Now, you guys probably went further. Is there a pattern to this? What happens in the second quadrant over here? I don't have it enough of it here. But we get negative root 3 over 3. Sorry, negative root 3, I'm sorry. Negative 1 and negative root 3 over 3, right? And then it's The pattern repeats itself. Okay, for this, could you plot me the tangent of 90 degrees or of pi halves? Could you physically plot that on a graph if I asked you to? Why not, Rafa? It's undefined. Now, today, we're going to take all of this and we're going to see that, hey, the other trig functions, once we can graph sine and cosine, if you can remember or even have written down these root 3's and undefined stuff, then we're going to be golden. And it's actually pretty easy to knock out. So, we're going to start 4.6. I'm going to push it back. I want you guys to remind me in 10 minutes. 10 after. We'll do those questions real quick. Okay. We're going to graph the other trig functions. And as long as you're comfortable with sine and cosine, the other ones, they follow the same exact idea. Except there's some little weird things. Remind me real quick before we start writing them. Sine and cosine, the period is what? 2 pi is the typical period of those things. So, we're going to jump out. Sine and cosine were defined the whole way around the circle. There were places on the unit circle where tangent doesn't work, yeah? What are those places? So it's up and down, right? Because wherever the x-coordinate or the cosine is 0, you can't do the tangent because sine over cosine is broken. Which means there's places where my function is undefined. So we're going to use that in our mind here. And we're going to start our first section. Let's graph tangent. And we're going to see a few little pieces that I'm going to try to tie together. First off, tangent is even or odd? Odd. Tangent, sine, cotangent, secant are all odd. The fact that it's odd means it reflects over what? The origin. Now, if we were to try to graph tangent, and I suggest we try, I want you to make a nice little table for me. We're going to graph the parent. So, quick example. I want you to make the table, and we're going to see some issues with it. I want you to graph, via the table that we're about to make, y equals the tangent of x. And we're going to do things a little bit different. For tangent, there's not as many obvious choices where nice values spit out. Because I'm going to be honest, I don't think root 3 is nice. I don't think root 3 over 3 is nice. 1 is, but that's the only one that's nice. I'm going to pick your x values for you, and you're going to see something pretty cool work out. I'm trying to say the best way to do this. I'm just going to give you points. There's going to be some weird ones that you're going to have to rely back on. I want you to do the tangent at negative pi halves. I want you to do it at negative pi fourths. I want you to do it at 0. I want you to do it at pi fourths. And I want you to do it at pi halves. Okay. Once you have it, I want you to attempt to sketch it. And then I'm going to come around and be real judgy about them. I just want to see where you're at. How do you try to deal with it based on stuff we've already seen? You'll have a couple minutes to try this. If you need help getting your table set up, would I be able to? Probably. Cool. I'm here. Your neighbors are here. Complete the table to the best of your ability. Complete the graph to the best of your ability. There's some old stuff that we've already seen that shows up in here. I'll give us a couple minutes. Now, notice in this problem I have chosen, and you may not quite understand why yet, but I've chosen values that spit out real nice stuff. I don't want to have to graph root 3 or root 3 over 3, but I'm totally cool graphing negative 1, 0, and 1. Okay, when we move to the graph, there's something that we've seen this year that you might have overlooked. I'm going to put these on here, and I'm just going to do it like I always do. So here's negative pi halves and roughly positive pi halves. There-ish. Does that look right to you? Close enough. And then that means that these other little ticks are the places where I need to put my points, right? Okay. 3 of these things are doable, and they're nice. I can plot the point negative pi fourths and negative 1. We'll say it's right there. I can plot this point, 0, 0. And I can plot this point here. That's a good question. That's a good thought as well. Now, how close can you get to either positive pi halves or negative pi halves until you actually break your function? Which, when I say break the function, what am I referring to? What makes it undefined? When cosine is 0, right? So imagine, and I'm just going to have to draw on the board so that they can see it, but this question's weird, and I love it. So here's a unit circle. I know that when I get all the way up to here, it breaks. So, odd question, I'm expecting a bunch of answers. How close can I get to it before it breaks? Everybody agree that I get infinitely close. As close as I possibly want. Until I actually get to that point, it's still defined. Okay. Does anybody remember us talking about any sort of function this year where a part of the graph gets infinitely or arbitrarily close to a value, but never quite reaches it? Oh, my asymptotes. Okay. Asymptotes happen in that exact same way, right? When we found the asymptotes of our rational functions, it's at the zeros of the denominator, where it tried to make us divide by 0. How do we represent an asymptote on this? How did we do it on our graphs before? One more time. Just a vertical line, right? So check it out. I don't remember what color I use. I'm going to use orange today. I know I'm never going to touch that line. And I'm never going to touch that line. Never. Okay. Anywhere else in that first little piece that we looked, is it ever going to be 0 between these ones? Or does tangent ever get to 0 as I get closer and closer to that pi halves number? I start dividing by something smaller and smaller, right? Because it's getting near 0, cosine does. What happens when you take some value that's almost 1 and you divide by smaller and smaller stuff? Say it again? Are you saying curve? Kind of. How would you like it to curve? So it depends on what side we're looking at. Ask your calculators real quick. If you're in degrees, change it to degrees for me. This is going to be easier to type in. Let's get a couple values real quick. I want you to find the tangent of 89 degrees. Okay. Do it again with 89.5. Tangent of 89.5 degrees. Are you 114.5? Okay, do it 89.9. We're at 114 before. We're getting closer to 90. 517? Holy cow, do 89.99. I bet it's 5117 is my guess. That was, okay, I'm wrong, but that's all right. What happens every time you get a little bit closer? It gets bigger. And how close can we get? So how big should it get? Infinitely big. Like, as we look at it, check it out. I'm going to start here, and I know that as I go toward it, I'll go back to red. On this side, I do see a vertical asymptote, where my function increases without bound is the way we word that. So I know it's going to come up like this, and it's just going to blast up. Now, I didn't take the time to measure it like directly, but I bet at pi thirds, this is probably pretty close to root 3 over 3, or root 3, I'm sorry. Like, that's an ugly decimal. I don't want to graph it. What do you think happens if we get close to negative 90, or negative pi halves in this case? It does the same thing. It just gets smaller and smaller, and in fact, it gets infinitely small. I see this function is stuck in between those two pieces. Now, harder question. On your unit circle, there's 4 quadrants, right? Which quadrants am I in on this graph? From negative pi halves to pi halves. First quadrant for sure, and the fourth. Now, as soon as I make it past pi halves, like, I don't care where we are, let's pick an angle really close to it. Once I'm past 90, what's one little tiny tick above 90? 91 is pretty close. Could we get closer than 91? 90.1, could we get closer than 90.1? 90.01 or 90.001. Ask your calculator real quick, what's tangent of 90.001? Really negative, right? So check this out. Can you guys tell me, just based off of reason, where's the next undefined spot on my graph? What's the distance between these undefined pieces? It's pi. So if I go another pi and I put it like here-ish, and I'm just eyeballing it, not labeling it, you just showed me that it's super negative to begin with, right after this. What do you think it's going to do? And it'll probably do the same thing over here until it gets to the other one. We have just discovered the graph of pi with, even cooler than this, a conceptual or a concept from calculus is how we just worked that out. You just did calculus, whether you're aware of it or not. You did. Okay, looking at this. From just this picture, we're going to detail some stuff, and we're going to try to make sense of it. Can you tell me how big of a piece in which x values would I have to range to be able to just pick it up and put it right back down so the graph replicates? How wide is each section? It goes from negative pi halves to pi halves, right? That's the section. How wide is that? Too big. It's pi, isn't it? Negative pi halves, so add pi halves. Yeah, it's pi. Gosh, what do we call that smallest piece that I can pick it up and paste it, and it just continues the graph? Not the jump yet. These are my jumps. Oh, one more time. The period. Check it out. Based on just what we've done, what is the period of tangent, the parent function? Pi radians. That's the period of tangent. It's pi, not 2 pi anymore, just pi because of that undefined nonsense. Okay, other pieces that we might care about naturally. This one's a little harder. Can you tell me the domain of the function tangent x? Which x values can I not plug in? So you've identified 2 of them, because I've only shown you a little part of the graph. How far could I graph this? Like I've already showed you, I've gone from pi halves to 3 pi halves, right? How far to the right could I go? Forever, right? Like as far as I want. How many vertical asymptotes are we not allowed to plug into this function then? Infinitely many. Do you guys want to start listing all infinitely many of them? Yeah. I don't, and I don't think you really do either. Man, so we need a way to write this. Okay, we are going to be notationally heavy here because it's super convenient because the wordy version's awful. I'm allowed to pick any x for my argument such that x cannot be equal to something. Every x except infinitely many of them, right? So here's how we need to reason this out. Give me the first easy asymptote that you see. Pi halves. X can't be pi halves. Okay, and then if I want to go further, whether it's a positive or negative, doesn't matter. If my first asymptote is here, how far do I go until I get my next asymptote? And then could I go another pi? Could I do this n times? As long as n is any number, it would land me on an asymptote, right? So let's just say it's pi halves plus, what number did we just say we could use? What letter? N pi. If you start at pi halves and you add pi n times, you're always going to end at an asymptote. Every single time.
And how did you figure out that it repeats like that?
Because when I graphed the second part, and we got, I just said 90 point whatever, we saw it was super negative.
There is a second part? That second line is like a...
This is me extending it further. So this is like my 90.01. Then I bet here we'd be right at pi. And it'd be 0 again, because it'd be 0 over negative 1. And then if you went all the way to like 269 degrees, or yeah, 269.99, you're going to see it blows up to infinity. It just keeps doing this over and over. Okay, if I ask about the domain, I'm probably going to ask about the range. What y values get hit here? How do I write infinitely many y values with no restraint? All reals. And I'm going to be more specific. I'm going to say y is in the set of, with that fancy epsilon, real numbers. Okay. Other things worth mentioning, but I'm not going to like talk them out. Where did we start? On our most basic. What's the furthest left of that first period that we look at? Negative pi halves. And where do we start? It's kind of weird because we don't really start there because it's undefined, but that's our first asymptote, right? Now, as we look at these, we have everything that we need about tangent. It is 100% only by convention, and just because this is what everybody agrees to like present this as at first, we start with this period only because it's right around the origin. Could I have started with this one and got the exact same answers? Or one way over here. I would have got the exact same answers. We would have seen the same pattern happening. We just want to start in that nice spot. Now, the cool thing about this is that it doesn't really change after we've done this. So, we're going to graph one together, but first, you're going to answer one of those 4 questions. Cool. So we're going to graph a nasty one together and see if we can't make sense of it. Okay, I'm going to get this set up. I'm going to just give you like the big moment here. Everything that we did before, B, A, C, and D, all those things are still enough, like they still apply. Amplitude doesn't make sense to talk about as the same, but steeper would be like the taller, and less steep would be shorter. We still have reflections, all those things. So without going through the list, I just want to see if we can replicate what we've been doing with sine and cosine to make sense of something. So let's make up a function. So example, graph, and we'll graph this one, and then we will move to sketching. And they're kind of be sketches, kind of. Help me make an ugly tangent. What do you want the first number to be? 5. Plus, let's say it's 3 tan of, what are you thinking? Seven x, let's say plus pi inside. That looks like an ugly function, kind of, or terribly. Can I change a 7 to something a little bit nicer just for now? I'm gonna change it to a 4. Only because if we overcomplicate it, I don't know that we gain anything extra from it, but I do want the complex version. Okay, so let's just think about this. When we looked at this asymptote, it happens when what is equal to negative pi halves. If I wanted to figure out where this thing didn't work, what is the argument of this function? So when the argument was equal to negative pi halves, it broke my function, yeah? Now, if we extend that, is there an argument on this? And whenever I plug in some x that makes this equal to negative pi halves, it breaks my function, right? So we're going to switch the order a little bit, but check it. Let's start, and really, this is my left asymptote. And we'll just say left vertical asymptote. I know that tangent breaks when I try to make it negative pi halves. So the only thing different about this is my argument's a little grosser, right? Let's set the argument, which is 4x minus, or plus pi. Set argument, and then we have a notation issue. I want to say set it not equal to negative pi halves. Now, in my mind, that's how I think of it, because it's not allowed to equal it, but we're still going to solve this not equation. And this is just going to tell me, oh, here's my first asymptote. What is the argument? Can you guys solve this equation or not equation, depending on whether you like the not equal to part? Can you solve this? Solve this for x. Yep. Okay, what's the first thing you did? You subtracted pi, so you got negative 3 pi halves. And then you multiplied it by 1/4. Negative 3 pi eighths. Are you guys okay with that? Okay, so I know that my function breaks when x is, and I hate this notation. I don't know that anybody else does this. Did I just say negative 3 pi eighths? Okay, this is the first place I'm going to put here. 3 pi eighths. And I don't even have to do any work because we just found the x value that breaks it. When we say it breaks the function, it means that when I plug it in, it spits out what? Undefined. Please don't do this, but I totally get it. I lied. I'm going to write the word. Undef. People are going to be tempted to do this. I won't fault you, but it's not right. Okay. Now, when we set up our tables with sine and cosine, once we knew where we started, what else did we have to find? We found the period. So let's knock that out. I'm going to put little stars next to each of these. Okay. For the period, what's the regular period of tangent? It's just pi normally, right? And for tangent, it's just pi. And I saw where you're going, Sean, and you're right. Instead of doing 2 pi over b, we're just going to do pi over b. Because it's the same thing. It's being adjusted the same way. What is b in this case? 4. Now, realistically, the period's only there so we can figure out how much we need to jump by. How do we determine the jump? You take the jump by taking the period that we had and divide it by 4, which is pi fourths divided by 4. I want you guys to complete the table and sketch this for tonight's homework. We know the next value. Just to make really sure, the next one you should get negative pi eighths. Is that right? I don't think that's right. Oh, it's just pi, right? Cool. I'm going to let you use your jump here. We'll pick up right here tomorrow. Try this problem. Later, Raiders.